3, 2, 1. Hello, chemistry peeps. Here is your video on everything D5 and D6 antiviral meds and the environmental impacts of medicines. We started this in class. We didn't get to it. So here is your fast and furious D5 and D6. Essential ideas are on the screen. This is what IB expects us to be able to talk about by the end of my rambling video. So quick review of viruses versus bacteria. Remember that bacteria are living and viruses are not. So bacteria are composed of cells. They have cell walls, they have cell membranes, they have DNA and RNA. They go through transcription, they make proteins and enzymes. They eat food, they make babies. Viruses are not the same. Viruses are not considered living because they are not composed of cells. They cannot reproduce themselves. They don't have cell walls. They do have a protein coat. These protein coats are called capsids. They are made of little protein pieces called capsomeres. They do have either DNA or RNA, but they don't have both. And we'll talk about the difference between the DNA viruses versus the RNA viruses in a little bit. What viruses do is that they inject their genetic information, either that DNA or that RNA, into their host cells. Then the host cell goes and does all of those processes that the virus can't do by itself. This is an example of a bacteria cell that is covered in all of these little viruses that are called bacteriophages. That might be an A, I'm not sure. Bacteriophage. Phage for short. So usually we just call them phages. So all these little guys that are stuck on this bacteria cell, all these little guys are bacteriophages. And what they do is they bind to receptor proteins on the cell wall of the bacteria, and then the DNA from the virus is secreted out of the protein coat down into the cell, the host cell. That DNA is then incorporated into the DNA of the bacteria cell, and the bacteria starts making all kinds of virus stuff. Over here, we have another example. So this big cell is a human T cell. It's part of our immune system, and all these little yellow guys are human immunodeficiency virus, HIV, that are infecting this T cell. Well, actually, I can't tell. They're either infecting or they're budding off. They might be HIV that's about to pop out of this T cell and go infect another one. Regardless, it's a bad thing. We'll talk a lot about HIV and T cells toward the end of the video. So quick look at these viral not life cycles. So lytic cycle versus lysogenic cycle. So both of them start with virus binding to receptors on the cell, injecting DNA into the cell. That DNA is then incorporated into the host cell's DNA. So now we've got viral DNA. In this example, it's a bacteria, but the same thing works with human cells as well. So we have this viral DNA, and the viral DNA is now part of the host cell's DNA. And so the host cell, in just taking care of itself, also ends up taking care of the virus. And so we make copies of the virus DNA. We make copies of the virus proteins, and then these pieces and parts get put together into all these tiny little virus babies. The cell then lyses, which is why we call it the lytic cycle, and all those little bacteriophage babies are released out into the environment where they can go and infect more cells. The other cycle, the lysogenic cycle. So what happens here is the virus binds to the receptors on the cell. We inject our DNA or RNA into the cell. It is incorporated into the host cell. But instead of right away making virus parts and pieces, we instead just be quiet for a little while. It kind of goes into hibernation in a way, where the virus DNA is part of the host cell's DNA, but it's not been activated. So we're not We're not using the virus DNA to make proteins, to make virus pieces and parts yet. But what is happening is this cell with the virus DNA gets bigger, and then it makes babies. If it's a bacteria, it goes through binary fission. If it's one of our cells, it goes through mitosis. But we are making more cells. The cell is growing and dividing, and every one of the resulting cells has copies of the virus DNA. And so HIV is particularly bad because HIV can sit in this lysogenic cycle for years, 10 years. And so you can imagine the number of cells that are produced through mitosis that all have copies of the virus. And then at some point, something triggers the viral DNA, it does get activated, and we end up in the lytic cycle. And so all of the cells, thousands or tens of thousands of cells, are now all producing viral DNA and viral proteins. And so thousands or tens of thousands of cells end up making these new copies of the viruses that are released either into the environment or into the biological system, the body, and they can go and infect all kinds of other cells in mass. And so even though the lytic cycle looks worse on the picture with that exploding cell, the lysogenic cycle really is scarier for us. So thinking about those not life cycles of viruses, our antiviral meds try to interfere with different parts of those cycles. So we're going to look at those over the course of the next couple of slides. First, we're going to talk about what would be better. So it's actually really hard for us to treat viruses because we can't kill them. We can't use antibiotics because antibiotics interfere. Antibiotics like penicillin interfere with cell wall production. Viruses don't have cell walls, so antibiotics don't do anything for viruses. With viruses, it's actually easier for us to prevent infection with vaccines. So we can give a human a vaccine. They're usually just pieces of the protein coat of the virus, none of the DNA, not the RNA, just pieces of the protein coat. The immune system learns what that protein looks like, knows that it's bad, and so when you get the real virus, your immune system knows how to shut it down really fast. And so it doesn't have time to get into cells. It can't make lots of virus babies. If you want an interesting story about the brilliance and horribleness of Edward Jenner, who developed the first smallpox vaccine in Europe, you can Google that. Edward Jenner, wonderful, brilliant, horrible person. But we have vaccines due in part to Edward Jenner and his brilliant horribleness. But I'm not going to go off on that tangent because I'm trying to get this done quickly for you so that you are not sitting here listening to me ramble for too long. So these are 4 different places where we are looking at interference with medications now. But these certainly aren't the only possible places that we could interfere. And so you and your fresh minds should really be thinking about what other parts of the viral cycles could we interrupt, could we interfere with to prevent infection from continuing in its course. So these 4 ways each have their own slide coming up. So that first way, we can prevent the virus from attaching to the host cell. So you have that host cell. Here maybe is the receptor and the virus sits there. If we could make some kind of medicine that sits on that receptor, that virus comes along, there's no place for him to sit. No virus can attach to the receptors. That means that the virus cannot get its DNA into the cell. Infection is prevented. Unfortunately, this is super slow. It's really, really expensive. And so we don't actually have any medicines on the market right now that work this way. But it certainly is a great way that we could prevent viral infections. We're just not there yet. A second place where we're able to, or we are actually able to interfere, is the uncoding process. So we have host cell, we have that receptor, virus comes along, virus gets into the host cell. And now we need to take apart these proteins so that the viral DNA can get out. If we can prevent the virus from getting out of the protein coat, if we can stop the enzymes that allow that from happening, then the DNA can't get into the host cell. The host cell isn't making new viruses. Two kinds of medicines that we have on the market that work this way: amantadine and rimantadine, which is also known as flumidine. These are good for treating cold and flu, except most of the cold and flu viruses are resistant. Here's amantadine. This one is rimantadine. And you can see that there's a lot of similarity. This chunk is really the only place where the two are different. Otherwise, the structures here are pretty similar. And again, these would be great, except most of our viruses are resistant. Another place where we are actually having a fair amount of success is by preventing the synthesis of the viral components. So we let the virus into the host cell. The virus can get into the host cell's DNA, but we throw in these medicines, acyclovir and zidovudine. I'm probably saying that wrong. Zidovudine is this one. Acyclovir is this one down here. And what these guys do is they look a whole lot like the components of DNA, the nucleotides. So we know that there are 4 nucleotides in DNA: adenine, thymine, cytosine, and guanine. That's a C. That's a G. And these two guys look a lot like guanosine. So you can see the similarities here. You can see the similarity. This one is not quite as similar. Some similarities here. This part's different. Acyclovir versus guanine. And then under my thing here, you can see this one is also different. So what happens is these guys get incorporated into the DNA. They're used when copies of the DNA are made. They're used when messenger RNA is made. And instead of this making it work correctly, this messes it up. And so even though we have copies of the viral DNA being made, it's made incorrectly. And then those copies can't make the proteins right. And so we have very ineffective viral proteins, can't make those protein coats the right way, and the viral DNA totally doesn't work. And so these guys do a good job of messing up the viral DNA and the viral proteins so that the infection cannot continue. Have lots of luck with herpes, chickenpox, and shingles. These are actually the same virus. This is more common in kiddos, and this is more common in the elderly, caused by the same virus, though. And then this guy, zidovudine, we have actually had some luck treating HIV with this guy as well, and we'll talk about that again in a couple more slides. The final way that we have right now for using our antiviral medications is to just stop the viruses from getting out. So we prevent the release of the virus babies, so the virus can get into the host cell. The host cell totally makes the virus proteins, the viral DNA. They are assembled inside the host cell, but then they can never get out. And so this prevents infection from spreading. So that the cell that's been infected is a loss, but at least no further cells are being infected. This works by inhibiting this enzyme called neuraminidase. I had to practice that a lot. Neuraminidase enzyme is one that you can see down in this picture. We have the virus getting into the host cell. Viral DNA is incorporated into the host cell's DNA. That DNA is used to make all kinds of virus proteins and viral DNA, and then it's packaged up. And then what usually happens is the virus is then, it buds off the host cell and is released to go and make another cell get sick. This guy, neuraminidase, just prevents this step from happening. So virus gets in, virus makes virus babies, but all the virus babies get stuck inside the cell. None of them get out. So again, this cell is a loss, but at least we're not sending out any more viruses to go infect more cells. Tamiflu, which is known as oseltamivir, and then Relenza, zanamivir, I didn't practice that one enough, clearly, help with true flu treatment, not true fleetment, flu treatment and prevention. You have probably heard of Tamiflu on the market. So this one is oseltamivir or Tamiflu. This one is zanamivir, also known as Relenza. How they are different, and this, my arrow is pointed to the wrong way. It should be pointed here, not here. So this ester group needs to be hydrolyzed into a carboxyl group. You can see over here, we've already got the hydroxyl group. Here, we don't yet. And so this guy, Tamiflu, is actually inactive when it first enters the body, but it is hydrolyzed. This chunk is chopped off. We throw a hydrogen on instead. And so this part of oseltamivir ends up looking far more like zanamivir as soon as it gets into the body. And again, ignore my arrow, it's pointed to the wrong place. This is the ester that needs to be hydrolyzed into that carboxyl group before it is active. Sadly, this guy, Tamiflu, we have a lot of resistance already, and so he's not as effective as it used to be. This one, the resistance hasn't popped up quite as much yet, but you can guess that it's probably not going to be too far into the future, given how these germs work. So now we're going to move away from the different processes that can be interrupted in those viral, not life cycles, and instead talk specifically about HIV because it is such a problem for us humans in society. So HIV, human immunodeficiency virus, is the virus that humans can get. It leads to this syndrome of symptoms, acquired immunodeficiency syndrome. So HIV causes AIDS, human immunodeficiency virus, acquired immunodeficiency syndrome. So we're going to look at some of the challenges that HIV presents to us, the medical community, pharmaceutical companies. How do we prevent it? How do we treat it? It's really hard. And these are some of the reasons why. So first of all, HIV copies itself super, super fast. 10 to the 10 copies per day, every day. It's kind of crazy. And so you can imagine that if there are a few viruses, it wouldn't be too hard to have enough medicine to capture them. But if you're looking at these guys replicating themselves at a rate of 10 to the 10 every single day, quantity-wise is overwhelming. Another big challenge that we face with trying to solve the problem that is HIV is that HIV infects helper T cells. So these are part of our immune system, and they do a lot of stuff for us. They basically initiate immune responses for pretty much everything. So helper T cells, you'll have one, it gets activated, it makes a bunch of babies. All of these guys go and do what this example cell is doing. So this example helper T cell, and again, during an infection, you have oodles of them. As it says, when a virus fragment is detected, it divides, and then all of those T cell babies, helper T cell babies, go and take care of all of these jobs. So one of the jobs is to activate killer T cells. These are also known as cytotoxic T cells. Because they mature in the thymus. This guy down here is a B cell because it matures in the bone marrow. But all of these are considered white blood cells. So these are all blood cells. These are all in the large family of white blood cells. So helper T cells activate killer T cells that will then literally kill cells that are infected with the virus. And if the cell that has the virus is dead, then the virus can't use that cell to make virus babies. So we are preventing the infection from spreading. Another thing that helper T cells do is that they activate these B cells, plasma B cells, and their job is to make antibodies. Be careful, antibody is not the same as antibiotic. So we make antibodies with our B cells. Antibodies are these little proteins. They are these little Y-shaped proteins, and what they do is bind to viruses or bacteria or fungal spores, whatever it is that's making you sick. An antibody will bind to it. If an antibody is stuck to the virus cannot bind to the receptor cells of the cells, or the receptor proteins of the host cells. And so the virus cannot get into the host cell, which means the virus can't take over. And so the infection is stopped. So antibodies we make. Remember, antibiotics, these are compounds that are made by fungus, like penicillin, and they prevent bacteria from making cell walls. So antibodies, we make ourselves. They bind to viruses or bacteria or whatever else is making us sick. Helper T cells tell the B cells to make the antibodies. Helper T cells also tell macrophages, which are our big blobby white blood cells that we most commonly think of when we think of white blood cells. So macrophages, their job is to eat things. And so this phage means eat, gobble. And so what a macrophage will do is it'll engulf, here's a virus covered in antibodies. And so the macrophage will eat up that virus, or the white blood cell, the macrophage will gobble up, digest, and kill the cells that are infected with the viruses. So these macrophages basically eat the stuff that's making us sick. Digest it, take it apart so it can't make us sick anymore. Helper T cells also tell us when we're not sick anymore. And so these suppressor T cells will then tell things, quiet down, we're fine, the virus is gone. So you can imagine that if HIV gets into these helper T cells and starts killing them, incapacitating them, taking over the processes, then none of this can happen, which means that any little thing is going to make us super, super sick because our immune system has not been told that we've been infected. So this is a big challenge with HIV. We can't just go and kill all the cells that HIV is infected, because then we essentially kill our entire immune systems. Big problem. Other things that make HIV particularly challenging, it can remain dormant in that lysogenic cycle for years and years and years, like up to 10 years, which means that people are HIV positive, but they're not symptomatic, which means that if they've not been tested, they don't know that they have HIV, and they're spreading it to partners without knowing. And so in terms of epidemics, this makes it particularly challenging for us as a society to deal with the epidemic of HIV, because that lysogenic piece of the cycle. And then another thing that makes HIV crazy difficult to deal with is it's a retrovirus. Retrovirus means that it carries RNA instead of DNA. So here's HIV. It's a retrovirus. Inside is not DNA but RNA. So the virus binds to the receptors on the cell wall. If we're talking about HIV, this is a helper T cell. Receptors on the helper T cell are what the virus binds to. Endocytosis pulls the virus in, that uncoating piece that we talked about, where the protein coat falls apart. The RNA, not DNA, but RNA is released into the cell. RNA cannot incorporate into the host cell's DNA. So what has to happen is we go through this process called reverse transcription. This enzyme, reverse transcriptase, is also brought into the host cell by the virus. Reverse transcriptase is an enzyme that basically goes backwards through the process. So usually we have DNA, and then we use our enzymes to make messenger RNA, and then we use our messenger RNA on a ribosome to make the protein, right? So we go through transcription and then translation, biology review. What happens with HIV and other retrovirus infections is the RNA that's brought into the cell has to get turned into DNA by this enzyme reverse transcriptase. And then that DNA gets incorporated into the host cell's DNA. And then you go through the normal process of making messenger RNA. This is virus messenger RNA. It's used to make virus proteins. It's packed into the protein coat. And then we have a new virus. HIV is the example we're talking about now. So the problem with this guy, reverse transcriptase, is he's a terrible, terrible enzyme. He doesn't do his job very well at all, which means that when we go from that viral RNA to the DNA, a lot of mutations are allowed. And these mutations mean that the proteins look a little bit different all the time. So it would be amazing if we could have a vaccine for HIV that would notice what those proteins look like. So you could take just that protein, inject it into humans, and then the human immune system would say, oh, that's a bad protein. I should attack it as soon as HIV gets into the body. The problem is these proteins look a little different all the time because this mutation rate is so crazy, crazy high. So HIV being a retrovirus makes it particularly difficult for us to vaccinate against because the mutation rate is so incredibly high. Any protein that we see on HIV today is not the protein that we're going to see next week. And so a vaccine for one particular protein is not going to help us because it's not going to look like that in a week or a year. However, we do have that medicine zidovudine. We talked about it a couple pages ago. That helps to inhibit reverse transcriptase. It inhibits it, it doesn't shut it down completely. So we can't eliminate HIV, but we can at least slow it down. Unfortunately, just slowing down a virus increases its ability to become resistant to the medicine. So even though zidovudine is being used now, it's probably not going to be super effective for much longer. Resistance is increasing. Here's zidovudine. We also talked about it with preventing synthesis with those guys that look a little bit like the components of DNA and RNA. So when we do use zidovudine is only to try to prevent resistance from building up too quickly. So if a person is symptomatic, if a person is suffering from AIDS, we'll go ahead and give zidovudine along with some other medicines. We call it a cocktail. It's a combination of lots of antivirals, some interferons, some other medications to slow the virus down as much as possible. We also give it during childbirth. So if mom is HIV positive, we can do this cocktail with zidovudine for mom, and that should help prevent the baby from contracting the virus during childbirth. The virus cannot get across the placenta, so the baby in utero won't be HIV positive, but childbirth is messy. There's a lot of blood, and so it's actually fairly easy for the baby to contract HIV during childbirth. So if we can suppress the virus a lot just during that time, mom is still HIV positive, but maybe we can prevent the baby from contracting the virus. Some social pieces about why HIV is really hard for us to deal with globally is that it's expensive. And even though here in the United States we have money, treatment is very, very expensive. People who have HIV without insurance are going to have some difficulties getting treated. Other nations around the world where there's not a lot of money are going to have a very, very difficult time getting treated. Another piece of the challenge is that historically, HIV hasn't really been something that we've focused on because the populations that it tended to infect the most were not populations that we necessarily focused on, unfortunately, horribly. We're certainly better now, but 30 years ago, 40 years ago, back in the 80s, the homosexual population was not one that was given a whole lot of respect or time or energy or money. And since HIV was something that was more common in homosexual men, is more common in drug users, it wasn't something that we focused on trying to treat or prevent. That's better now, but that social cultural issue certainly slowed down our progress with HIV medications. And then of course, when we look at those poorer nations on the planet, people who are likely to get HIV are also usually not very well educated. They don't know that HIV is a thing. They don't know that AIDS is a thing. They don't know how to prevent it. They can't afford to prevent passing the disease. And so this lack of education, lack of money definitely increases the epidemic in poor nations around the globe. And you already know this, but there's an increased risk with drug use, sharing needles, and then unprotected sex leads to more HIV transmission. So on that sad, depressing note, we're going to flip over to topic D6 and look at the environmental impacts of medicine. So it's mostly about medical waste. And medical waste we also refer to as xenobiotics, xeno meaning foreign, biotics, these bioactive compounds that are released into the environment. We also call medical waste PACs, pharmacologically active compounds. For a long time, we didn't have a whole lot of regulations. And so these guys were really just thrown away, like dumped in a trash can, sent to a landfill. And so these medicines, all kinds of medicines, seeped out into the groundwater, ended up in ponds and lakes and plants, and ended up moving up the food chain. Did change the metabolism of some organisms, change some of the biological processes of some critters on our planet. Also led to bacteria being more resistant. And we talked about this with penicillin, but it's worth a reminder. So resistant bacteria pop up for multiple reasons. One is when we overprescribe antibiotics. If I'm a fussy mom and I take my baby to the doctor and I'm like, she's sick, and the doctor's like, it's just a virus, she'll get over it. And I'm like, I want my medicine. The doctor might just give in to make me shut up. And so we do tend to overprescribe antibiotics just to make the mamas happy, even though we know that they don't do a lick of good for viral infections. Of course, not using our antibiotics correctly can also lead to resistance. You're prescribed 10 days of antibiotics, but you feel better after 7, so you stop taking them. Those last little strongest of the bacteria are still alive, and so these are the ones that have the babies, and then all the babies are strong and able to resist the antibiotics. Another piece is hospitals and pharmaceutical companies, and they're better now, but in the past, extra stuff or old stuff was just thrown away. And so we ended up with a lot of antibiotics released into the environment. Again, ended up in soil and plants and water and animals. And the more antibiotics there are in the environment, the more resistant bacteria are going to pop up. The worst offender, though, is probably agriculture right now. Agriculture accounts for 50 to 60% of all the antibiotics used on the planet. Farmers give antibiotics regularly, daily, to their cows and their pigs and their goats and their chickens to prevent diseases from popping up. And it's important to the farmers to be able to harvest as many animals as possible. It's how they make their money. It's how they make a living. The problem is, though, that giving all of these animals antibiotics all the time leads to a whole lot of antibiotics left over in poop. And that poop gets into the dirt, into the soil, into the water, it goes everywhere through the food chain. Those antibiotics stay in the meat and then end up being eaten by us humans. And so we're spreading these antibiotics out a lot. There are more regulations now, but not everywhere. Not everywhere in the world. Places like China can pretty much do whatever they want to. There are far fewer regulations there than here in the States. So agriculture, big part of the number of resistant bacteria that we have popping up. All of this waste is problematic because of this idea of bioaccumulation, biomagnification. So we might have a little bit. This picture is particularly for DDT, which is a pesticide, but the idea relates to medicines as well. So we have just a few little pieces of medicine floating around, getting incorporated into the producers. But our primary consumers have to eat a lot of producers. It's not like this one fish eats one plant in his lifetime. He's eating a lot of plant. And so these medicines, these xenobiotics that are in the environment are going to accumulate in the primary consumer. And then, of course, the secondary consumer, this guy doesn't just eat one fish in his lifetime. He eats a lot of them. And so all of the stuff that's accumulated in this fish is going to accumulate in this one. All of the fish that he eats, he's going to get. And that tertiary consumer, again, he isn't eating just one of these guys. He's eating lots of them who ate lots of these guys that ate lots of those guys. And so the concentration of the medicine or the pesticide is going to increase drastically from one of these trophic levels to the next. So bioaccumulation, biomagnification is a big problem when we're looking at medical waste. So to build another different kind of medical waste, so not necessarily a medicine, but well, it could be a medicine. So medicines that are radioactive, treatments for cancer that involve radiation. We have a lot of diagnostic tools that use radioactive compounds. All of these materials can also get thrown away as waste. Radioactive materials we refer to as radionuclides or radioactive isotopes. They're unstable. Their nuclei just don't stick together very well. And so they go through decay, alpha decay, beta decay. A lot of energy is released. Gamma radiation is that energy that's released when these nuclei of unstable atoms are going through decay. So this is all nuclear waste. We have a couple different categories for our nuclear waste. We have low-level waste, which is not terrible. They have fairly short half-lives. Remember, half-life is the amount of time that it takes a radioactive material for half of it to turn into this stable isotope that it decays into. So if you have a fairly short half-life, or there's little energy being released during decay, then we're not too worried. The amount of energy isn't problematic. The energy is spent fairly quickly. And so low-level waste products tend to include syringes, other tools, tongue depressors, and paper towels, and vials and jars that we would use to hold on to these radioactive materials that we use for cancer treatment or diagnostic tools. All of these that are low-level waste, they're contaminated with this short half-life radioisotopes. We just store them for a little while in a container that is lead or some other kind of material that prevents that energy from escaping into the environment. You just store it until the radioactivity has decreased to a point where it's not dangerous anymore, and then you burn it or dump it into a landfill. Hold on, my kid is messing with the cat. Ethan, I'm making a video for school here. Let him go. Sorry. All right, moving on. Then we also have high level waste, and that should say high, not low. Is it wrong on your paper too? Yeah, so it should be high level waste for the H, not the low. Clearly, I was not paying attention there. So make that high level waste. This is stuff coming out of nuclear reactors. It's going to have to sit in cooling tubs for years and years and years because the energy is so intense. There's so much heat created. We just have to keep these things cold for a long, 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 long time. Years of keeping cold. After it's been kept cold for years, it's calmed down a little bit. We bind it up either in glass or rock, synthetic rock. And then we bury that. So it doesn't actually go away. It's not totally safe anymore. We just bind it up into glass. We bind it up into rock. We bury it and hope it stays in the glass or the rock. Radioactivity is super problematic because this energy that's being released, this high intensity energy, can lead to mutations in DNA, which causes cancer. Radiation poisoning, all kinds of terrible things. This in the environment, definitely a problem, not something that we want to let happen. Another kind of waste product, moving away from radioactivity stuff, great scientific vocabulary, radioactivity stuff. We're going to look at organic solvents now. So a couple examples of organic solvents: benzene, chloroform, carbon tetrachloride. So these guys, we use to dissolve things that water can't dissolve. So if we have something like oil, some other kind of non-polar compound that we want to dissolve, water won't do it. And so we have to use benzene, we have to use chloroform. If I'm trying to get an organic non-polar compound out of a seed or out of a plant, water is not going to do it. And so I use these organic solvents instead. Unfortunately, these guys that are really good at dissolving organic compounds are also particularly toxic to humans and other animals. They wreak havoc on our respiratory systems, on our nervous systems, can lead to all kinds of crazy brain cancer. They also mess up our kidneys, livers, reproductive organs. So really, really bad for animals. They're carcinogenic. They cause cancer. They're also flammable. So you have to be super careful about storing them. Otherwise, you just have these amazing, like, spontaneous combustion messes that you just don't want to have. So all kinds of problematic. We have these other solvents, carbon tetrachloride, these other chlorinated alkanes that are released into the environment, float up into the upper layers of the atmosphere, and then start attacking ozone. Ozone, where we breathe, is bad for us. It is a pollutant, but ozone in the upper layers of the atmosphere helps to deflect some of the UV radiation that's coming from the sun. If we don't have enough ozone in the ozone layer, more UV radiation from the sun gets through, and then there's more skin cancer. That's not what we want. So we should really do a good job of protecting the ozone layer, not allowing these chlorinated solvents to escape out into the environment. One option, an alternative to these organic solvents, is supercritical carbon dioxide. So kind of cool. This CO2 that we can, at extremely high temperatures and crazy high pressures. So we're making it super hot. It wants to be a gas, but we're also squeezing it super, super tight. So it would rather be a solid, but it's super hot, so it can't be a solid. But we're squeezing it together, so it doesn't want to be a gas. We end up with this stuff called supercritical fluid. So it has properties of both gas and liquid. and it's just CO2. And so not nearly as terrible as benzene, chloroform, carbon tetrachloride. Um, um, and we use it now for dry cleaning because it does blast oils out of clothes pretty easily without using soap. We use it to blast caffeine out of coffee beans to make our decaf coffee. So a lot of uses already put into place. And we're looking at using the supercritical fluid CO2 more and more as an organic solvent to extract these compounds that we want, these organic compounds that can't be extracted with water. We can extract it with this supercritical carbon dioxide instead. Better for us than the benzene, the chloroform. So those are some of the problems. Now we'll look at some of the solutions. So green chemistry is simply the idea that we want to reduce the environmental impact of these nasty chemicals by minimizing how much we use and minimizing how much we make. Makes sense, right? One of the ways that we calculate how hazardous something is, how big the impact is, this idea of atom economy, which is the efficiency of some kind of chemical procedure that's being carried out in the lab. So we look at the ratio of the molar masses of the target compound only. So not all the products, but just the product that is bioactive, just the pharmacologically active product of a chemical reaction. But we put the ratio over the masses of all the reactants because I want to see how much stuff I have to use to make what I want to make. And so our target product over all the reactants. And if we have a 1 to 100, it's probably not worth making. If we have a 10 to 100 or a 50 to 100, then maybe it's worth the risk. And so this idea of atom economy, am I getting a lot of product for the reactants that I'm putting in? Is it worth it? I have not to date seen a problem in option D about this, but just in case, the formula is in table 1 of your data booklet, but under A5, not in the D section. So you can find this formula, table 1 of the data booklet in section A5. So a little bit more green chemistry. We are almost done, my friends. So instead of chemists making these chemicals, we're actually having these bioengineers make GMOs that will make the chemicals for us. So GMO, genetically modified organism, usually gets a really bad reputation in the media. Everyone's like, anti-GMO, I don't want any GMO in my food. But here's the thing, GMOs are amazing. GMOs make human insulin now. A long time ago, diabetic people, it was very expensive to get insulin. It was usually pig insulin. So pigs or sheep were killed. We smashed up their pancreas. We extracted the insulin, probably using some of those nasty organic solvents that we talked about a little bit ago. And then human diabetic patients would take pig insulin to try to treat their diabetes. Pig insulin is close to human, but not the same. And so a lot of people had allergies. A lot of people had problems. People with diabetes did not live for very long. But now we have these amazing bacteria, E. coli, and we have blasted into the bacteria the DNA that codes for human insulin, the protein insulin that humans make. And so E. coli have the human gene for human insulin. And so we have this big, beautiful flask, and we fill it full of food and bacteria that have the insulin gene. We keep them fed and warm in an incubator, and those E. coli just make lots of babies, and they make lots of insulin, and all the babies make insulin. And then for far less money, much easier, we have human insulin. And so we don't have the troubles with allergies. We don't have that mismatch of not quite the right insulin trying to treat diabetics. They have human insulin being made by these genetically modified bacteria. It's better. And we're working on trying to apply this idea, this bioengineering, to more medicines. And so instead of a chemist mixing together a bunch of chemicals and having all kinds of nasty side products pop out, we instead are trying to get these bacteria, E. coli, to make these medicines for us. So one example that we have going on right now, Tamiflu, one of those medicines that helps us with preventing the spread of the flu virus, is shikimic acid. And so we can use shikimic acid to make Tamiflu. We used to get shikimic acid out of anise, and so we had to use some of those nasty organic solvents to get the shikimic acid out of the anise. It was expensive. Anise is expensive to harvest. It's expensive to grow. You don't get a whole lot of the acid out of the seeds. So instead, we have blasted the gene that makes this shikimic acid, took it out of the anise plant, blasted it into bacteria. And now we have these beautiful, ginormous flasks that sit in a lab, and we have bacteria and we have food, and we keep them happy and warm, and they can just pump out all kinds of shikimic acid, which then chemists can use to make Tamiflu. At some point, hopefully we'll get to a point where the E. coli can make the Tamiflu for us, where the E. coli can make all kinds of amazing things for us, because there are fewer side effects. There are fewer nasty processes, fewer steps that we have to go through, less of those organic solvents that we have to use to make our medicines. And it's better. It's better for the planet, better for us, better for our patients. So that is the end of option D. I hope you enjoyed our crazy long rambling video. You can also read the two chunks in the textbook, pages 745 to 750 on antiviral medications, and then 751 to 757 on environmental impacts. Pages 750 and then 757, the last pages of those two chunks, have practice problems if you want to use those to review. And on that note, my friends, we are calling it a day.